Hello everyone, my name is Ganesh. Today I am going to present my presentation on the topic of zeta potential analyzer, and the content of this presentation is introduction, definition and factors affecting zeta potential and how to measure the zeta potential and theories related to zeta potential like DLVO theory and what are the applications of zeta potential and what is the main conclusion of a zeta potential, what is the purpose of conclusion can be discussed later in this presentation. So we start with our introduction. Zeta potential is electrostatic potential at the slipping plane of a particle in suspension. It is a scientific term for electrokinetic potential in colloidal dispersion. It is generally represented by Greek letter zeta, hence we call it zeta potential. In other words, it can be also said as the electric potential at the boundary of the double layer is known as the zeta potential of this particle, and this typically ranges from plus 100 millivolts to minus 100 millivolts. It generally indicates the stability of a colloidal suspension and is important for the maintaining particle dispersion. Coming to its definition, zeta potential, it is the potential observed at the shear plane, which is also known as this slipping plane. Zeta potential is also called as electrokinetic potential, which is defined as the difference in the potential between the shear plane and electroneutral region in the motion of the plane. Here in the figure, we see that this is the electroneutral region plane and it is the slipping plane. The difference in the potential difference between these two planes is called zeta potential. And the zeta potential is more important than the non-S potential because the electric double layer also moves when the particle is under motion in the zeta potential. Whereas in the non-S potential, the electric layer doesn't move. The non-S potential, it is the potential of the solid surface itself owing to the presence of a potential determining ions. Non-S potential or electrothermal potential is defined as the difference in the potential between the actual surface and the electroneutral region of the solution. And coming to the factors affecting the zeta potential, mainly the two factors affects the zeta potential. One is pH and another one is thickness of a double layer. So firstly we'll discuss with the pH. In aqueous medium, the pH of a sample, one of the most important factors that affects its zeta potential. Zeta potential versus pH curve will be positive at low pH and negative at high pH. See, coming to the figure here, which is plotted against the zeta potential versus on the y-axis and pH in the x-axis. Zeta potential is taken in millivolts and pH is taken in the x-axis, and so at low pH the zeta potential value is positive, and as the pH increases the zeta potential going into negative values, and there is a certain point where the zeta potential is negative, is zero. That point is called as that point is called as isoelectric point. This point is a very important point for the practical consideration. And coming to the second factor which affects the zeta potential is thickness of a double layer. The thickness of a double layer, which is the difference between this electroneutral region and this slipping plane. The higher the ionic strength of this atom, more the double layer becomes. The double layer compresses. So the valence of the ions also influence the double thicknesses. Coming to zeta potential measurement. So in the zeta potential is not directly measurable. It can be calculated using theoretical models like electrokinetic phenomena and electroacoustic phenomena. So we'll discuss firstly we'll discuss electrokinetic phenomena. Electrophoresis, the movement of a charged particle related to liquid. It is suspended in under the influence of an electric field. Zeta potential of a dispersion is measured by applying an electric field across the dispersion. Particles within the dispersion with a zeta potential will migrate towards the electrode of opposite charge with a velocity proportional to the magnitude of the zeta potential. The velocity of a zeta particle in a unit electric field is referred to as electrophoretic mobility. The zeta potential is related to electrophoretic mobility by the Henry equation. Henry equation is which gives a relationship between electrophoretic mobility and zeta potential, which is known as UE equals to 2 epsilon z f of ka by 3 eta m, where UE is electrophoretic mobility and z is zeta potential and epsilon is a dielectric constant and eta is viscosity and f of k is a Henry's function. And coming to the second phenomena, which is known as electroacoustic phenomena. In the electroacoustic phenomena characterize the dynamic mobility of the particles in colloidal system. In this method, high frequency electric field is applied to the samples and causing charged particles to oscillate and to produce sound wave of the same frequency. The oscillations, which is known as dynamic mobility of the particles, is described by its magnitude and phase angle. The sound wave is detected by and analyzed to determine the motion of the particles. And coming to the next measurement process, how it actually measures. First, actually, the sample is prepared and it is loaded into the cell, and the electric field is applied and the data is analyzed. So the dilute and prepare the sample accurately and load the sample in this cell and apply the electric field across the cell, and record the data in the computer using the proper softwares and determine the zeta potential. The equipment, this is the equipment schematic, how actually how the zeta potential actually works. This is a laser which emits the beam of light through the cell. Cell holds the sample, laser beam interacts with it. After cell, it passes through detector, and through detector, it passes through digital signal processor, which is known as DSP. And through DSP, it passes through computer, where the data is analyzed and the zeta potential is calculated. And there is a beam splitter, which splits the laser beam into two parts, one for the sample and one for the reference. And optics, this is called combining optics, which adjusts the light path to the director of the accurate measurements. And coming to the next is zeta potential cell. There are two types of zeta potential cells are available. One is folded capillary cell and another one is a universal dip cell. In the first picture is showing is folded capillary cell, and the second picture is showing is universal dip cell. The solvent in the universal folded capillary cell can be used as water or alcohol. The volume of this folded capillary cell is around 0.75 ml, and which is made up of polycarbonate material. And the second cell is universal dip cell, which is the solvent can be used as a water or alcohol in this cell, and the approximate volume of this cell is around 0.7 milliliters. And coming to the next, DL Vivo theory, which is given by the four scientists, namely Derjanguin, Langew, Verwey, Orbeek. These four scientists have developed this theory in the 1940, which deals with the stability of a colloidal systems. This DL Vivo theory suggests the stability of a colloidal system determined by the sum of van der Waals forces, attractive forces, and electrical double-layer repulsive forces that exist between the particles as they approach each other due to the Brownian motion they are undergoing. The van der Waals forces depend on chemical nature and size of the particle. The electrostatic repulsive forces depend on density, size, surface of charge, and thickness of a double layer. Methods for stabilizing colloids. Physical stability can be achieved by maintaining the particle in Brownian motion and provide electrical charge on surface of dispersed particle. The like charge on the particle will prevent this coming closer together and thus maintaining a Brownian motion. We know that always like charges always repel each other. So as when they repel each other, they follow random motion, which is known as a Brownian motion. And coming to the next point, maintain solvent sheath around the particle. The solvent layer prevents the particle coming closer and also maintain Brownian motion. And coming to the working principle, particle in suspension develop a surface charge and attracting layer for counter ions, which is also known as electrical double layer. Zeta potential is the electrical potential at the slipping plane in this layer. Electrical field is moves charged particles and their velocity is measured to calculate the zeta potential. High zeta potential ensures the stability, while low values of indicates the flocculation. And the applications of zeta potential are in pharmaceutical industries and wastewater treatment in chemical industries and cosmetics and nanotechnologies and food industries. Coming to the pharmaceuticals, stability of drug suspensions and emulsions can be measured by this zeta potential. And wastewater, coming to the wastewater treatment, understanding the flocculation and coagulation in wastewater treatment is a very important parameter. And cosmetics are emulsions of stability for creams and lotions. In nanotechnology, it ensures the nanoparticle dispersion in solutions. and stability of food suspensions and emulsions in food industries. And coming to the importance of zeta potential, why should we measure the zeta potential? What is the importance of zeta potential? It actually surface charge and stability determines whether the particle will repel or aggregate. High zeta potential indicates the stability of a colloidal suspensions, prevents the aggregation. And the low zeta potential suggests that the particles are prone to aggregation, causing instability. And the main advantages of the zeta potential are quick analysis, non-destructive and versatile quantitative results. It provides immediate feedback on particle stability and sample remains intact with further testing, and it is a versatile, suitable for many industries requiring stability control and quantitative results. It provides a precise stability data for the control. And we know that every equipment has limitations and advantages. Same as in the zeta potential analyzer also have some limitations. The sample one is sample preparation. Contamination and improper dilution can affect accuracy. So ionic strength sensitivity is also one of the limitation, which high ionic strength impacts the double layer and affects the results. And material limitations. Unsuitable for highly conductive or irregularly shaped samples can affect the zeta potential. Temperature, pH, ionic concentration can affect the now, coming to the conclusion, zeta potential has been recognized as an excellent tool for characterizing the colloidal system. In recent years, the concept of zeta potential has been applied to areas beyond classical colloidal sciences and industrial processes. The expanding role of a zeta potential in pharmaceutical sciences is attributed to the advance in model instrument of zeta potential measurement and the rapid development of colloidal, and emphasize the interdisciplinary basic research. Zeta potential analysis is essential for accessing particle stability in colloidal suspensions. Thanks everyone for watching this video.